Welcome back. There we go, making sure that I'm recording. All right, so I don't know, it bothers me when I see that getting to be, even though, does it really make a difference if it's two shorter tapes or one longer tape? I kind of like it to be to the two shorter tapes. And so I am refreshed. This is the derivative. Sometimes you just need to stop for a moment. All right, so on the graph of the derivative, all of these correspond to values of the slope, right? That's what we get from the derivative, the value of the slope, the rate of change in our function. So right here at f prime of 0, this is 3, means our function has a slope of 3, right? Right here, there's a slope of 2. Right here, it's a slope of, no, can you see if I write a little darker? A slope of, I'm trying to find where the 0 is on this thing. That one is the slope of 0, because there's 0 right there. I just wrote the word slope over it. There's 0, right? So here m equals 0. And then here we have a slope of -1 because we're at -1. So this is pointing to this right there, right? And a slope of 0 again. And then a slope of 2's over here and a slope of 3, right? So those are the values of our derivative are the slopes of the original function, right? So kind of have those a little all over the place there. So it says that we start at 0, right? So from 0 to can you see the values there? 2. So that's 1 there. So from 0 to 1, we've got kind of a slope of 3 going, and then it kind of slows down to a slope of 2, right? And then it's slowing down, right, until we get to a slope of 0, right? So at 2, the slope is 0, right? You've got an x-intercept on your derivative. You've got a slope of 0, right? So then we're decreasing, right, because we're below the x-axis. So we were increasing because we were above the x-axis, right? So everywhere until we get to 2, we're increasing, and then we're decreasing until we get to 4. And this we have a slope of -1, right, and then back up to 0 for that minimum, right, and then we're above the x-axis, so we're increasing, right? So we're going to go from they're at 5, right? When x is 5, we've got a slope of 2, right? So when I get to 5, I need to have kind of a slope of 2 going there. I think my slope looks a little shallow. And then at 6, we have that gap there, right? Well, that gap isn't because there's a break in the graph. It just, we go from increasing to decreasing, and there is a vertical tangent line because of the cusp there, right? So we're undefined. That's why they're so far apart, because we have a slope of 3 coming into that x equals 6, right? And then we have a slope of -2, right? And it meets at a sharp point, so we have a vertical tangent line going there. Right, so that's why we have that break in our derivative, and then we're decreasing, and then we'll be increasing afterwards. My graph just kind of ends at 8 on this one, so but that function keeps going past 8, so I just added a little piece there. So the slopes of the tangent lines for our function should match the values of f prime of x for corresponding x values. Graph extreme inflection points, intervals where decreasing, increasing, concavity is indicated by the first derivative. Right? So if possible, determine the x values at which the function maintains a maximum or minimum value. And it's going to depend if this is an open or closed interval. All right, so if it's an open interval, the one side is going to keep, it's going to the left there, it's going to keep going down to -infinity. So that is no local minimum, no absolute minimum. And then to the right side, you're going to keep going up to infinity. But let's say this is a closed interval, and we're closed between 0 and 9, I guess, because I see 9 there. Then we would have an absolute max, and it looks like it would be the exact same thing occurring over in two different places, perhaps. Definitely, we would have an absolute max at x equals 2. Assuming I'm good on my slopes there, could also be at x equals 6 as well. Right? And then a minimum would be at x equals 0, would be the absolute minimum. Right? Because that would be the absolute lowest point. All right, so here's how you use the graph of the derivative to be able to graph your function. Because we're not trying to graph just a possible graph. We're trying to graph the graph that actually corresponds with it. Will we be perfect? Maybe not, but we should be pretty close. Sometimes I'm a little off trying to get my slopes in. All right, so, and we'll do a little bit with this in class on Monday. So you get just a little bit of practice besides just me telling you. All right, and so there's a relationship between our first, our second, and our original function. And a lot of times we'll be working with our original function to get the, our derivative to get to be able to graph our function. We won't really go too often from the second derivative. That's really tough. But we could go from the first derivative to graph the function. This one's going the other way. This one is graphing, and this is kind of what I had in my head when we were going over the other one. This one is graphing the derivative from the function. So there you're plotting out the slopes, and the slopes are the values for your derivative. So here at 1 we have about a slope of 4. So that means we're going to be at, our first value is going to be at 4. So at 0 we're at 4. Right? And then we have a slope of about 1 between B and C. So then B prime is going to be at 1. And at C there we have a horizontal tangent line. So C prime is going to be at 0. And then between C and D we have a slope of -1. So D prime will be at -1. And between D and E we have still a slope of -1. So E is going to also be at -1. But it was, it's not going to be a horizontal line, right? So it's probably going to keep decreasing a little bit. And then we have a slope of 0 there at 6. And that's going to correspond with that relative minimum there on the graph, and it's going to be an x-intercept for the first derivative. So here's how you can go from the graph to the derivative. And what you're graphing here is the slopes. If you go from the derivative back to the function, the values of the derivative are your slopes, right? So f of a prime is 4. That means that the slope at a is 4. So you can go back and forth between those, right? And I think this is a good place for us to stop. All right, and then I'll pick up with the rest of this, little bits and pieces, in class, and we'll do a little practice. So a little summary here of everything we've learned. Right, on your function, the zeros are x-intercepts of the graph. Where it's positive, the graph lies above the x-axis. Where it's negative, the graph lies below the x-axis. Where your first derivative, the zeros, the critical points, give you relative extremes. And it's a maximum if we go from increasing to decreasing. It's a minimum if we go to from decreasing to increasing. A positive sign study tells us where the function is increasing, and where we're negative on our sign study, that's where our function is decreasing. Our second derivative, the zeros, are points of inflection. Where the second derivative is positive, our function is concave up. Where the second derivative is negative, our function is concave down. Right? So a little review. We'll do the rest of this matching graphs and derivatives and functions and derivatives, and doing a little practice in class. And then we'll also be looking at something else, maybe on Monday. I don't know. We'll find out. All right. Well, thanks for watching this podcast, which was about 45 minutes. Whew. Boy, I can talk. Thanks for joining me, and I'll see you later. Bye-bye.